Okay, so I wanted to take a moment and talk about this week's activity that you will be downloading and filling in the blanks and then uploading for credit. What this activity looks at is it's identifying all of the bits and pieces that take place, such as reflection, radiation, diffusion, absorption, that the energy from the sun undergoes before it hits the Earth's surface. So we're looking at incoming shortwave radiation in comparison to the right-hand side of our diagram of our outgoing long-wave radiation from the Earth. So remember that it's coming in as a shortwave radiation from the sun, being absorbed by the Earth's surface, and then being re-radiated out as outgoing long-wave radiation. So what you're going to be doing is you are going to be looking at the diagram and you are going to be filling in the blanks. So for example, we see that we have, now I'm looking at the left-hand side here, so the incoming shortwave radiation. We have absorbed in atmosphere, absorbed at surface, and those two inputs can give us the total absorbed. So we can go ahead and take our absorbed by ozone and absorbed by clouds, dust, and gases to give us a total value of 22 absorbed in atmosphere. Okay, so you're basically going to be filling in the blanks and then providing your total reflected at the top versus your total re-radiation to space. Now, a little bit of hint. So the total reflected value and the total re-radiating to space should equal 100. And so I'll let you guys go ahead and plug away at this worksheet, and then you can go ahead and upload it for weekly credit. So before we move forward on atmospheric circulation, I want to go ahead and do just a little bit of review in talking about temperature concepts. Now, we spent some time at great detail talking about the 4 distinct levels of the atmosphere, identified thermally what's taking place, and chemically how those different layers are different from each other. So in moving forward and talking about temperature, we know that we identified sensible heat is what we feel versus temperature that can be measured as kinetic energy of molecules. So we feel the heat when kinetic energy is transferred from molecules to us. And we know that we can measure heat in degrees Celsius. We also can measure it in Fahrenheit or Kelvin. So those are the 3 different measurements that we can measure heat. Now, we did talk about latitude and how the distribution of incoming solar energy is different. We know that we have a surplus of energy between the Tropic of Cancer at 23.5 degrees north and at the Tropic of Capricorn at 23.5 degrees south. Okay, so we have this surplus of energy that's coming in, and that energy needs to be distributed across the globe. And so that starts getting into global circulation, but we do know that there is an energy deficit at higher latitudes. It's not the same intensity. So above 23.5 degrees north to 90 degrees north, we have a deficit. And from 23.5 degrees south to 90 degrees south, we have this deficit. And so the Earth is always trying to achieve balance. And so where we have greater value of energy, we want to disperse it to where we have lesser values. And so this is really going to feed into our global circulation. How does the energy from the sun move to higher latitudes? And that's through our global circulation. So we know that insolation decreases as we move away from the subsolar point. And it changes in the day length and sun angles with increasing latitude. Now, we did talk about this particular line chart. We're looking at months along the x-axis, and we're looking at location of latitude on the y-axis. And we're looking at Barrow, Alaska, Montreal, Quebec, Edinburgh, Scotland, New Orleans, Louisiana, and Salvador, Brazil. And these are different latitudes, and they depict the different temperature changes that we see and the location of where they are located on the Earth's surface, latitude-wise. We also see elevation in the information, but along the x-axis we have the months of the year, so going from January, February, March, April. So it really gives us a good indication of what significant influences that this particular location has. Is it located along the tropics where it's pretty consistent temperature around 13 degrees south? high elevation going to be an influence on a particular temperature that's measured at this location? Is this particular location located near the ocean where it's going to have regulated effects? And so these are all the things that we want to talk about in moving forward. Now we talked about altitude and how temperature decreases in the troposphere, and we refer to this decrease as the lapse rate between 3.5 and 6.4 degrees Celsius per 1,000 meters. Now this is going to be a consistent temperature change as we increase in altitude, and we'll talk about this much more when we start talking about weather and clouds. We know that the atmospheric density decreases with elevation, and we know that the thinner atmosphere can absorb less energy, therefore temperature drops with altitude. And as we move forward, we know that the atmospheric density at 5,500 meters is half of what at sea level. So a lot of the heavier molecules are held closer to the Earth's surface due to gravitational forces. They're heavier. So if we go ahead and look at a cross-section comparing two locations, we see Concepcion, Bolivia, and La Paz, Bolivia. We know that the latitude is very similar. They're 16 degrees and 7 minutes for Concepcion and 16 degrees and 30 minutes south. We know that the elevation, however, is very different. Concepcion is 490 meters and La Paz, Bolivia is 4,000 meters. So in looking at the comparison here, we see that the La Paz is in the blue line here and Concepcion is the red line. That altitude is going to have a huge impact on our temperature. And we also see the whisker charts showing us the max and mean and minimum temperature of these locations. And this is looking at the mean is where the line crosses our temperature line, and we see the maximum and minimum temperatures depicted on the chart below. We also see how the annual temperature range, we have 5 degrees Celsius versus 3 degrees Celsius, and our annual precipitation is half as much. So Concepcion is 121 centimeters, but La Paz, Bolivia is 55 centimeters. Almost half as less precipitation is falling in La Paz, Bolivia. Now, you should start to think, well, what would be the reason for that? Well, we did describe that the elevation is different in these two locations, so there must be another physical factor, such as is La Paz, Bolivia on a rain shadow? Are there multiple ranges that are causing the air parcels to rise and have that temperature fall out? These are things that we'll talk about in great detail. Other factors that we want to talk about when we're comparing locations is going to be marine versus continental location. So marine, meaning that it's located by the ocean. The ocean acts as this natural way to provide energy to make sure that the temperature is consistent. So it acts as a thermostat, making sure that the fluctuation in temperature really doesn't decrease much. So there's really no major span in temperature from the high point to the low point, versus a location that's away from the ocean that can moderate temperature fluctuation, and as a result you have these extreme temperatures. You have hot conditions in the summer and you have very cold conditions in the wintertime. Now when we talk about the ocean and properties of ocean, we know that oceans can help distribute energy, and we have ocean circulation that can help keep temperatures consistent. We'll talk about that in great detail. Land, however, cannot move, doesn't have ocean currents and channels and changes within the water to help mitigate temperature. And we know that the thermal properties of land versus water are very different. So we can go ahead and look at our temperature and precipitation charts for San Francisco, California, and Wichita, Kansas. Now, both of them are located at the same latitude at 37 degrees. One's at 37 minutes north, and the other one's at 39 minutes north. But notice that in looking at the red line on the two charts that we have huge fluctuation. We see San Francisco located on the west coast with the Pacific Ocean. We have Wichita, Kansas, almost center of the United States, where it's far removed from ocean influence. Now let's go ahead and look at our temperature range. We have The elevation of San Francisco is at 5 meters. The elevation at Wichita, Kansas is 400 meters roughly. We see the average temperature is roughly 14 degrees Celsius. The average temperature, annual temperature is 13 degrees Celsius. Annual temperature range is a range of 27 degrees. And our annual temperature range in San Francisco is 9. So San Francisco only fluctuates 9 degrees Celsius from its highs and lows, and that's pretty consistent. And that's the influence of the Pacific Ocean churning and mixing the water and keeping the conditions there very consistent, as a result to Wichita, Kansas, where it gets very, very, very hot in July and August, to very, very cold below freezing in the winter months. And this is going to be marine versus continental. Now, in looking at some of the detail specific properties about marine versus continental climate, we know that they're very different. We know that soil cannot mix and turn, and therefore it's going to have a very different specific heat as a result to water. So continental temperature conditions are more extreme. Land warms and cools rapidly. We have less evaporation and a lower latent heat. We know that the surface is opaque and the land has a lower specific heat, so as a result of that, it heats up really fast and cools down really fast, and the land can't mix between layers. The water, on the other hand, our marine climates and temperatures, we know that temperature conditions are moderate. Water slowly warms up and cools slowly, but it also has the mobility function that it can mix and turn, and that water has a higher specific heat. And that's going to be a huge factor in comparing, locations of two cities. Are they located near a large body of water that's going to have more moderate temperatures, or are they going to be far removed in the middle of a continent? So specific heat. The specific heat, the amount of heat per unit mass required to raise the temperature by 1 degree Celsius. We know that land versus water has two very different. And we also see these in our isotherms. So these are our lines of temperature that we see on maps. Now, the isotherms, we can follow an isotherm, which is this red line here, which represents temperature for 15 degrees Celsius in July. So notice that as the isotherm, as we move over the interior of this hypothetical continent, the temperature increases quite a bit. And as we go out over the water, it is regulated. The same thing can be said following 15 degrees Celsius in January. Our isotherm, as it comes across the interior of the continent, it drops down drastically due to the thermal properties of land. And we have a smaller shift over the water, so more moderated. And then when moving back to altitude, we can also see that altitude is going to have a huge influence as we see temperature, going back to our Concepcion, Bolivia, and our La Paz, Bolivia example. Now this is going back, we've already looked at this already, but we can see that the northern hemisphere difference is in the amount of continental land versus ocean. So the northern hemisphere has 39% land and 61% water. And the southern hemisphere has 19% land and 81% water. And this is going to have a huge impact when we start talking about global circulation, because we do know, we just talked about, land has different thermal properties than water, all going back to specific heat. Okay, one other factor that we need to talk about, these are more local factors that are going to be influencing temperature from a location, is called the urban heat island. And this is going to go back to the type of physical features and characteristics such as concrete and asphalt versus green grass and vegetation. And it's really going to influence the thermal properties of an urban area. And so scientists find that temperatures are a little bit warmer because of the thermal properties of the surfaces in an urban environment. And there's also less water on the surface. And so we have darker surfaces, which is really going to increase air temperature when we are in an area that's more urban. So larger cities are going to have some more heat effect as a result of that, and that's known as the urban heat island. And we can go ahead and see a sketch of an urban heat island profile where we see late afternoon temperature on our y-axis and we have our different properties on our x-axis.